Bismillahirrahmanirrahim. Welcome to the third session of data structures and algorithms. Primarily, we have two agenda points for this slide set. One is doubly linked list, other one is double-ended queue. And after doing these two things, we'll be studying uh, another variation of queues, which is called circular queue. And towards end of today's session, we should be able to introduce another data structure, which is very different than the kind of stuff which we studied in our previous session and this session. That is called tree. So let's start with a quick recap of what we did last time. And so if you are like able to recall, we talked about linked list in our previous session. And more specifically, we talked about its implementation. We talked about different characteristics, different properties of a linked list. And we talked about different operations which can be performed in a linked list. So I had recommended towards end of the previous session, which was a recorded session, to implement linked list on your own. It might be taking a little more time than expected, but it is extremely important to understand the linked list so that you can have a very good grip on data structures implementations in the coming days. Linked list, having a good grip on linked list is a prerequisite of implementing any decent data structure in this course. So if you have not started with the implementation of linked list in your programming language, which we are like preferring Java now, so please start it today. And towards somewhere mid of this session, we'll be talking about the first programming assignment, which is going to be a graded assignment. And that also involves a lot of stuff related to linked list. So what we, besides studying data structures in our previous class, we talked about some operations which can be performed on any data structure. And more specifically, we talked about operations to be performed on linked list, and we tried to estimate their time complexity in the form of big O. So whenever you are asked to find the time complexity of a given algorithm, that means that you have to derive, or you have to compute, or you have to estimate the time complexity in the form of big O. So what is the time complexity to add an element at the end of the linked list? So in our towards end of our previous session, we said that this is big O1, and big O1 is a representation, if you are able to recall from our previous discussion. So we use this specific notation of big O1 to notate constant complexity. By constant complexity, we mean that the number of steps required to complete that algorithm do not depend on the size of the input. So irrespective of how big or small is the data structure, the number of steps required to do that thing will remain constant. And the reason it is big O1 in this case, in adding an element at the end of the linked list, is that special thing which we talked about in our previous session, and that was that we are going to have a special pointer. We call it a tail pointer. So tail is a pointer, it is a reference. This will take care of the last node. So if you keep on remembering the reference, remembering the address, that who is the current last node of the linked list, we can just append a new node with that reference, which is termed as tail. But if we don't have this tail reference, then we'll have to scan the whole linked list. So same way, we also talked about what is the time complexity to remove an element from the end. That means that you have to get rid of the last node. What does that mean? So in terms of a linked list, getting rid of the last node means somewhat like this, which we can see here on the screen. And that is that if this is the start point, so we have a node, it contains some data and it has a next reference. So next knows the address of the next node. That second node knows the address of the third node. So that's how the linked list is chained. And if this third node is the last node, then this will be, its next will be pointing to or referring to null, which means that there is no further node at the end of the third node. Now, if we have to get rid of this node, so our objective is to get rid of this node. So in order to do, and we know that this is being referred by this reference, which is tail. So we don't have any mechanism to go back straight away from tail. So what we can do is that we start from the start point, from the head of the linked list. So step by step, we keep on hopping through the linked list. And as we reach to the second last node, we just change its next pointer to null. So its next compartment starts pointing to something which is null, which means that we are essentially removing this reference. So the third node has been delinked from the second node. So in that case, our now resultant linked list will only be containing 2 nodes. But in order to do this whole thing, we'll have to hop through, we'll have to go through all those existing nodes whose count is variable. And we use small n to notate the number of total nodes in the linked list. So in this case, the time complexity is going to be big O of n, and n is the number of steps, number of nodes which are there in the linked list. Okay. What is the time complexity to add an element at the second last position? Now, because we know that how to walk through the linked list, so we can, we'll have to start from the head, and then we'll have to keep on hopping through the linked list in order to locate the second last node, and that will also lead us to big O of n complexity. What will be the time complexity to remove an element from the second last position? The same case, we'll have to again hop through the whole linked list. We'll have to walk through all existing nodes of the linked list, which are n, and our time complexity will be big O n. Okay. So this is the kind of stuff which we tried to do in our previous session as well. Do we have any questions so far about the stuff which we discussed in our previous week?
For that, I have no question. It was all clear and
Thank you.
To be honest, I haven't watched all the lecture, the whole, but this is very clear for this topic.
Okay, thank you very much. So we can move forward, right? So what we have studied so far is the simple linked list. So an extension or a variant of single or simple linked list is doubly linked list. And the reason we call it doubly linked list is that it knows address of the next node. So all these forward nodes, all these forward edges, or all these forward references are same as those of the previous linked list. On top of that, we have some additional references whom we are terming as the previous references. So second node knows who is its first node. So it holds address of the previous node. This node holds address of the previous node, and this holds address holds holds address of the previous node. So in that, and if you look at the first node, because the first node, so there is no previous node, so its previous is null. If you look at the tail node, there is no next, so its next is null. Okay. So now if we try to look at the structure of one node, so one node contains three parts. So these 3 parts actually make up one node. So we have this data part. The central part is the part which we call data part. So we can essentially store some data over here. So this is somewhat similar to what we saw in our previous linked list. Then we have a reference, which is next. So the second compartment knows address of the next node. So these two components are exactly similar to those which we already saw last week in our simple linked list. On top of that, we are adding the new reference, which is this one, and this is what we call the previous reference. So this previous reference will have address of the previous node. So in our implementation, in our code, we'll have to modify the class node a little bit. We'll have to add this additional reference in order to get things done. And then most of the logic will remain same. Other than that, other than that part where we were only manipulating next, now we'll have to manipulate previous as well. So let's see these things in action. So if you look at this code snippet, so this essentially defines one node of a doubly linked list. So as part of the code over here, we can see that these three attributes or three data members are here in the class node. First one is the data part. Second and third are next and previous, and type of both of them is node, which means that they can hold address of another object of class node. And then we have two constructors over here. This is zero parameter or zero argument constructor, which simply initializes data to zero, and it initializes next and previous to null. So it creates one empty node. Or if you know the data, you can create a node with data D. So D will go in data and next and previous will be null. So that will just create one independent isolated node. And then you can use these parameters, these member functions to change or retrieve the next and previous pointers. So if you have to set next of a node, you can call this function set next, or you can call this function set previous, or same way in order to retrieve or in order to fetch the next or previous node of a given node, you can call either of these two functions, get next and get previous, and they'll return as a node object. So what I would strongly suggest is that step number one is to complete your implementation of the previous linked list. Once you are done, slightly modify that code and you will be implementing the doubly linked list, because doubly linked list is a simple or natural extension of the simple linked list, which you would have implemented before this implementation. So let's try to analyze the implementation of doubly linked list, that what will be the cost or what will be the amount of time associated with different operations of this doubly linked list. So what is the time complexity to add an element at the end? So if you are able to recall the time complexity to add an element at the end in a simple linked list, that was big O 1. And over here, our logic will remain same because we know the tail pointer, we know the tail reference, or we know the tail node. So we can simply add a new node towards end of that node, and that will take us to the cost big O 1, which means that in constant number of steps, we can add a node towards end of the doubly linked list. So what is the time complexity to remove an element from the end? Now, this is going to be slightly different than a simply linked list. And let's try to analyze that why is it different. So let me try to draw both of the linked list with three nodes each. So this is a simple linked list. So this node points to the second node. Second node points to the third node. And the third node points to null, which means that this third node is the last node, versus a doubly linked list, which will be looking somewhat like this, that each node is different in structure. It will be having three compartments. So because this is the first node, so its previous is null, and its next is the second node. So second node will also be having three compartments. So previous over here is the first node, and we have a third node over here. So the second node has its next as the third node. The third node has its previous as the second node. And the last pointer over here is that next of the last node is null, which primarily represents that this is end of the linked list. Now, if you try to do this third bullet operation in both of the linked lists, let's try to analyze that what is the time complexity to remove an element from the end. So even if we know that this last node is tail, we can't access the previous node because there's no previous pointer. So in order to get to the second last node, because our objective is to make it null, and when we make it null, then essentially we are overwriting this pointer and this last node gets disconnected. So in order to do this thing, we'll have to start from scratch and we'll have to hop through the linked list in order to reach over there, right? So that will take us all those steps. We'll have to spend n steps in order to get over here. So if the linked list is very large, we'll have to spend the same number of jumps or same number of hops as those of number of nodes in the linked list. So that was the case. And in our previous slide, we said that the cost of removing the low node from the end is big O n in a simple linked list. But now if you look at the green part, so we know the tail over here. So if we know the tail, so we can very easily, in one step, we can go back using this previous pointer. This previous pointer is a facility which we have in doubly linked list. This facility was not given to us in the uh, in the previous linked list. So in big O1 or in one step, we can go back and we now have access to this node. And once we have access to this node, what we need to do is that we can disconnect this one by changing its next to null. So we make its next as null, and that disconnects this doubly linked list from the last node. And in two steps, we are now done with removing the node from end of the linked list. So what the question is that what is the time complexity to remove an element from the end of the linked list? The answer is big O1, which was big O n in a simply linked list. So what is the time complexity to add an element at the second last position? So we use the same analogy as we have just seen in removing the last node. We can get it done in big O1, which was a big O n kind of case in the previous example. And the time complexity to remove an element from the second last position is also n, because we can just take one step back using the previous pointer or using the previous reference, and we can get things done in big O1. So an ungraded homework is that extend your implementation of a simple linked list, and try to convert that into doubly linked list and make sure that all those operations of adding nodes at different endpoints are being performed within these bounds. By bounds, I mean the complexity, the big O's. So if you write a function, if you write a method to add an element at the end, your function should make sure that things are getting done in constant number of steps. So one intuitive hint is that if there is no loop involved or if there is no recursion involved, then things can be done in big O1, which means that there are fixed number of steps which you need to perform. And that's what we call constant complexity. And that makes that function efficient in terms of number of steps, particularly in the case when we have a large number of nodes in the data structure or in the linked list. Okay, and please feel free to interrupt me if you have any questions. So we are done with doubly linked list. So it's very important to implement it on your own in a programming language of your comfort, so that you can attain a very good hands-on knowledge of that particular data structure. So now we're moving to another data structure, which is called double-ended queue. So sometimes it's abbreviated as DEQ as well. So DE stands for double-ended, and then we put this short Q at the end. So which means that if there is, it's like a queue, but it has a slightly different behavior. And when we say it's a queue, so that means that it has two endpoints. One is the start site, and the other one is the other endpoint, which is end. So we can insert elements at start, or we can remove elements from start. Same way we can insert elements from end, and we can remove elements from end. And that's why these four operations are the primitive operations which are supported in a doubly linked list, in a double-ended queue. So one of them is add at start or add at end. So these are the two endpoints where you can add new elements or new nodes, or you can remove from start, or you can remove from end. As the names of these functions give us some hints, so that means that we need to have two pointers over here. One is the start point, other one is the end point. So we need to keep a track of that, where is the start, where is the end. So if our user asks us to add an element at end, we'll have to use this end pointer. Or if the user asks us to add at start, then we'll have to use this start pointer to get things done. Now take a moment. This is an empty table. So we have many choices to implement a double-ended queue. So if we have to implement a double-ended queue in an array, which we actually did in our previous session. So try to estimate the time complexity of performing these four operations if we have to implement a double-ended queue using an array as underlying data structure. So before you dive deep into the time complexity stuff, let's have a quick recap of something which we discussed in our one of the previous sessions. So we talked about two kinds of data types. One is called abstract data type, and we notated abstract data type as ADT. So abstract data type is the conceptual data type which primarily lays down the rules or lays down the behavior of that expected data type. So in this case, this double-ended queue, which we write as DAC, is the abstract data type. Now, how to implement this abstract data type is going to be defined using a concrete implementation at the backend. And that concrete implementation at the backend is essentially what makes is our actual implemented data structure. So that concrete data structure at the back end, we don't have anything as such called double-ended queue, but we'll have to use one of these three possible implementation choices to make it double-ended queue. So it could be an array, it could be a linked list, it could be a doubly linked list. So I would strongly urge for those people who have joined in the live mode, they can spend the next couple of minutes. I can take a pause over here to try to fill this table on your own, and that should help us that whether you were able to recall those previous things which we have already done, but those things being put in a different order are making a new abstract data type, which is double-ended queue in our case. For all those people who could not join online and will eventually be watching this recorded video, you can also pause the video before you see the solution and try to estimate all these complexities on your own, just to make sure that you are on board and your answers match with what we will see in the next slide. So just take a small pause. So I'm taking a short pause for all those people who are here in the live mode. Try to estimate it on your own, and then we'll move forward. Okay, so will any one of you who are online would like to add anything on the answers? So if you look at this table, so this is now filled with answers. Let's have a quick discussion. So you might be able to recall our implementation using an array. So what is the cost to add an element at the start? If you're able to recall, we used to say in our previous session that this is big O N because we have to shift all those existing elements one step forward. So that takes us those n shift operations, and that's why the cost is big O n. In order to add an element at the end is constant time, is big O1. In order to remove an element from start, it's again big O n due to those shift operations. And in order to remove an element from end is big O1. So this is what we saw in the case of arrays. When we try to implement the same ADT or same abstract data type using a linked list as the concrete data structure at the backend. So add at start is big O1. We just like in constant number of steps, we can insert a node. This is what we coded in our previous class as well. We can add at end, which was given to you as the homework. And if you know the tail pointer, if you have the tail reference, you can get it done in big O1. But just a side comment, if you don't have the tail reference, then you will have to scan the whole linked list, and this entire operation will become a big O(n) operation. And just to keep it optimal, just to keep it efficient, we are using, or we are suggesting to use the tail pointer, so that we can get at least this one operation in constant number of steps. How to remove from start. This is also what we did in our previous class. We coded for this function, and it takes constant number of steps to get the existing node disconnected from the linked list. And remove from n takes big O n because we need to scan the whole linked list for that purpose. So what we have just seen today in our previous slides was that what is the cost of these operations in a doubly linked list. So doubly linked list can be used to get all these things done in big O1 operations, which means that as a relative choice, this is more attractive, this is more efficient implementation choice for implementing the abstract data type of double-ended queue, because all those four primitive operations can be done in big O1. So another ungraded homework is that because you would have already implemented these implementations of linked list and doubly linked list, so you can customize them, you can specialize them, you can cut some of the functions from there, and you can implement a double-ended queue using these four operations within these time bounds. Okay, now an extremely important thing is that your first graded assignment is going to be uploaded in a while today. But even if we like get little late on implementing or on sharing that document with you over Moodle and WhatsApp group, you can start working on the assignment or thinking about the set assignment straight away. There will be two tasks. For both of the tasks, you have to write Java code. And the first task is very simple, and that is that you have to complete your implementation of linked list on your own. And let's have a quick discussion that why this task is important, why we are assigning you this thing as a graded thing. This is an extremely important. So in my view, implementing a linked list from scratch is extremely important. This is one of the super important and parent data structures which you must have a very good hands-on. So if you get a very good hands-on or practical grip on linked list, all other coming data structures will become quite easy. But there is a side effect as well. If due to any reason, if you are unable to implement a linked list on your own, you'll face difficulties in the coming data structures, particularly different variants of linked lists and the kind of stuff which we'll see in our coming sessions about trees. So I would strongly suggest that please implement this linked list. And that's the reason that we are going to make it compulsory for the grading purpose. And it's if you have to like if you really want to understand data structures, you must have a very good hands-on experience of coding linked list from scratch. It might be taking a little more amount of time. That's fine. You can talk to us. You can talk to me. You already know that how to talk to me. So what I have done is that there are two alums students of computer science from third and fourth years. They've joined our group as teaching assistants. One of them is Safa, other one is Fatim. So both of them have volunteered to act as teaching assistants for this course. So they're part of the group. So I'll be introducing them formally over the WhatsApp group in a while. but you can also seek their assistance if you are facing any difficulty in coding your assignments. So the objective or the purpose of taking these TAs on board is to enable more support to you and make your entire learning experience more fruitful as far as particularly this implementation stuff is concerned. Then the second part of the first assignment is that you have to implement a polynomial calculator using multiple linked lists. So the document which we'll be uploading will lay down the details, but it is somewhat like this thing that your program, your assignment should be able to do this kind of thing. So for example, if I have a polynomial 2x plus 5x minus 10, and if I have another polynomial, which is let's say 7x minus 2, and if I want to add these two polynomials, so the answer, we should be able to compute their answer as a polynomial, and for that purpose, that's what we mean by polynomial calculator. So addition is one operation, you will have to perform another like couple of operations as well, and for that purpose you will need to use different linked lists. One linked list will be able to hold one polynomial. So we list down all those required details in the document. Please go through that document. And if you have any questions, you can get back to us through WhatsApp or any medium of communication you feel comfortable with. So, but the first graded assignment is now out. You can start working on this. Okay, another important thing is that please maintain the decorum, avoid cheating, don't lose your opportunity to learn and build confidence about solving relatively larger problems. We know that solutions of these assignments might be available online. If you try to use those online solutions and just submit them, they won't really help you in terms of your learning. And like major chunk or purpose of the course might be lost during this whole exercise if you don't do things on your own. So I would strongly suggest and request that please maintain the decorum. We are here to assist you in all possible ways. Please let us know if you face any difficulty, but I would strongly urge that do all these assignments on your own. Any questions so far?
Hello,
No,
doctor.
thank
Yes, I
you.
have a question.
Yeah, please go ahead.
I was gonna ask about the deadline for this first assignment,
Okay.
and how can we submit it? What's the procedures and steps and all the details?
Okay.
But if you're gonna send it later, it's no problem. I will wait.
Yeah, that's fine. I can like quickly explain. We'll include them in the document, but you will have to upload those assignments through Gaza Moodle, and I'll create a link over there. So there will be a link with the tag assignment one. You can go there and submit it. That's one thing. Deadline is going to be almost a week from now, but that's flexible. So in the next week, we'll be having another assignment. So if you start doing them today and spend a week and on your comfort and try to finish it within a week, that will be really great. But we know that like some people might be having difficulty in sparing time due to the unfortunate situation which we are facing on ground. So we will keep it flexible. But for all those people who have time and who can attempt it, so we would strongly suggest that you should submit it within a week, so that when we upload the second assignment, you should start working on the second assignment. Otherwise, the only difficulty which you will have to face, or those people will have to face who don't start on time, is that you'll be having a like a pool of multiple assignments at the same time. And so we'll keep those deadlines open till end of this semester. But strong suggestion is that get it done before the next assignment is released, which we are planning to release in the coming week. But we are also going to include all the submission details in the document. Does that sound okay?
All right. Thank you, doctor. Yes, that sounds very good. Very well. Thank you, doctor.
Thank you. Thank you. More than welcome. Okay. So we are almost like halfway of what we had planned for today. So the third data structure, which we would like to get in detail, and that is the last data structure related to queues, stacks, lists, and all those things. We call them linear data structures. So that is called circular queue. So by circular queue, we mean that this queue behaves in a circular fashion. So let's try to analyze this thing. So this is just a visualization of a simple array. If you look at the numbers which are written in red outside the circles, those are indexes of the array. So so actually this whole array is this whole queue or this whole data structure is somewhat like this in the back end. So there are there is 0, 1, 2, 3, 4, 5, 6, and 7. So these are the indexes of the array. So the 0 index contains 10, then we have 20, then we have 30, we have 40, and we have 50. So this is what is this data structure. The additional two things are that we have two pointers. So we have an end, which is being labeled as rear end. So this is being notated as at index 0 at the moment. Then there is something which is being put over here as front end. So the reason we call it circular is that if you have like few elements like this one, so then implementation is simple and it's somewhat very similar to that of a simple array. But if we add three more elements, so for example, we add 60 and 60, 70, and 80. So 60 goes here, front moves next. Then we add 70 over here, front moves next. Then we insert 80, so front is now pointing here at 80. So this front is gone and front is now pointing to 80. So if I try to add one more element, I don't have space. So question number one is that how to check that this circular array or circular queue or circular data structure is full. So if we now try to look at this whole thing, all those 8 spaces are filled. So there are different ways to do this thing or check this thing in implementation or in your code. So in our implementation or in one possibility, which we are about to see in the next slide, we are going to maintain a counter. So counter is initially 0. So as we add an element, that counter keeps on increasing by 1. And when counter becomes equal to the size, so if counter is equal to 8 in this case, then we should generate an error message that our queue is full and there is no more space because the underlying data structure is essentially an array. So now, because we are calling it a queue, so if you recall the stuff we studied about queues in our previous weeks, so in queues, we said that this is essentially a first in, first out data structure. It follows this FIFO protocol. So the elements which were added first have to go out first. So if we call a dequeue function, then this element has to go first. This has to go out first. So rear is essentially pointing to the element which has to go first. So once we dequeue 10, 10 will go away and rear should start pointing over here. And now if you look over here on this setting that when rear is pointing to 20, so the index number 0 is available for more insertion. And if we try to now add 90 into it, so we can conveniently add 90 and 90 should go to next to 80 because we are looking at this whole data structure in the circular fashion. So neighbor of 7 is 0. So 90 gets added at 0 because this is now available. And front now starts pointing to 90. So if you look over here, what is happening at the background is that 0 uh, is the new answer for index, but we have moved from 7. So what we do is that we add 1 into 7. So it gives us 8. So we divide it over the size, which in our case is 8. So we do 7 plus 1 mod 8. So 8 mod 8 gives us 0 answer, and that's how we compute the next index. So if we try to look at the implementation side of this story, So there are two ways. So that way is primarily on how we look at circular queue as an array implementation. We can alternatively implement circular queue as a linked list as well. So in that case, the small modification which we need to do over here is that the last node used to point in a linked list, this last node used to point to null. Now it is pointing to the first node of the linked list, and that's what is making it circular. So we can implement this abstract data type of circular queue using an array or using a linked list. So on the backend, in terms of implementation, if we are implementing an array to get this AVDT in place, so we need to have all those things which we saw in that green figure. So our class name is circular queue, and then we have this front and rear two integer pointers. And we have an underlying data structures, which is an array of size 10, and we maintain an additional attribute, which is count of number of elements which have been which are currently added in the circular queue. And then we implement these set NQ and DQ operations. We implement is full and is empty operations. So these two operations essentially help us to check if we can add or remove more elements. The queue is already full. So this is full function or is full method should return true. If it returns true, then NQ operation should not be performed. And if as is empty is the operation, if it returns true, that means that there is no element in the circular queue, then we cannot perform the DQ operation. So this is how the overall structure of the data structure circular queue should look like. Let's get in little more detail on implementation of NQ and DQ operations. So if you look at the NQ part, because we have an array of 10 integers, so we are passing this D to be enqueued or to be stored in the circular queue. So first thing which we do is that we check that it should not be full. Because if we check it, is it not full? If this thing is okay, then we do these things. Otherwise, we will just skip this whole logic because we won't be able to find the valid space inside the array. And the kind of logic which we just saw in that green figure is that we readjust our front, we add 1 into front, we divide it over the size, and we take the remainder, and that gives us the next front. So, and then we use that front as the index to store this D, which was passed over here from the caller of this function, and increment counter. So if this was the first element, then rear should also be moved from -1 to 0 because rear was initialized as -1 in the constructor. And if you try to have a quick look on the DQ part, so it's a flip operation of what we saw there. So if it is not empty, then that's the only case when DQ operation can be performed. So we're using this example -5 as something which is empty. So we say data of rear should become -5, which means that's not a valid item. We are just overwriting the valid item with -5, and we are decrementing the count. So if count has become 0 out due to these DQ operations, that means the array is empty, and rear and front should both be set to -1, so that they are not the valid indexes and we don't have anything inside the queue. Otherwise, rear will be adjusted like this. So I would strongly suggest that try to run these functions on your own later on paper using that circular array, and see how insertions and removals are being performed in the data structure. But before we move forward, let's have a quick look on both of these functions once more. Try to look at the structure of the function. There's no loop involved in DQ. There's no recursion in DQ. That means that all those steps which are here inside the function are constant. They are not dependent on how big or small is the array. And if you look at the previous one, NQ operation, same is the case over here. There's no loop, there's no recursion, which means that we're not like repeating some part again and again. That leads us to this clue, this hint, that the total number of steps which are being performed as part of this data structure are constant, and they're not dependent on how big or small is the queue. So one NQ operation can be performed in constant number of steps, and one DQ operation can also be performed in constant number of steps. So if we are using an array, which we were using in our like this recent example, so our NQ and DQ operation both can be performed in big O1 and big O1 over here. And what about linked list? So linked list is also, we've already seen things in terms of linked list that we can like perform some of the operations in a convenient way, and some of the operations might be needing more time. So try to recall that thing, that what will be the cost over here, and if you use a doubly linked list, what will be the cost over here. Now, another part of recap, which we have like discussed a while ago as well, that all these three choices on the x-axis, array, linked list, and doubly linked list, all of them are the concrete implementations of some abstract data type. So in this case, in this particular story which we are discussing at the moment, our abstract data type is circular queue, and we have a choice. So as a programmer, as a software engineer, it's your choice to analyze the complexity of different implementation choices and opt for the one which is the most efficient one for your case. So if you have to implement a circular queue, you first, before you start coding, you need to analyze that which of the implementation choice will take you how much amount of cost in terms of big O. So once you are like clear that what will be the cost, then you can make a choice. So in this case, all the choices are going to take equal number of steps. So then like so time complexity is equally good or bad for these implementation choices. Then we can go for some secondary choices, that which one is easy to code, which one is hard to code. Or another important thing, that array might not be a dynamic data structure. So sometimes we will have to fix the array size. And if you have to add more elements, then we don't have like that kind of flexibility to conveniently increase its size. So that increasing its size might be costing us some additional stuff. So those might be some additional or secondary constraints or considerations which you can keep in mind as a programmer. So that's it. We are done with the circular queue. So far what we have done is that so let's try to quickly list down the data structures which we have discussed so far. We started with simple arrays as the backend implementation. So this was one kind of, so these are all concrete implementations. Then with arrays, we talked about linked list. Then we talked about another variation of linked list, which is called doubly linked list, which has two pointers, next and previous. So these three essentially make up the concrete implementations, the underlying data structures which are being coded. So, but in order to, we use these different concrete implementations for different types of abstract data types. The first simplest abstract data type which we have studied so far is list. So we can create any type of list using any of these choices. Another another abstract data type which we studied in our previous classes was stack. Then we talked about an abstract data type which is queue. Then at the start of today's session, we talked about double-ended queue, which we abbreviated as DEC. And very recently, we have talked about another abstract data type, which is circular queue. So all what we have seen so far is that all of these red abstract data types can be possibly implemented in terms of any of those three underlying data structures. So if you try to map some combinations, so practically we have seen 3 times 5, 15 different implementation choices for those 5 abstract data types in total. So any comment or question, if you would like to ask anything? All right. So again, like the previous suggestions, ungraded homework is that try to implement all these data structures which we are studying. And that's the only way to become expert in data structures. Okay. Why I discourage GPT or like any AI generated stuff? So this is the experiment which I did a couple of months ago. So I have a colleague over here. His name is Dr. Imdad. So I posed a question to ChatGPT. I have 10 chocolates today, and I gave 3 to Dr. Imdad yesterday. So how many chocolates am I left with now? You can, like, on your own, you can try to understand the question and figure out the answer. GPT said, if you started with 10 chocolates and gave 3 to Dr. Imdad yesterday, you would have 10 minus 3, 7 chocolates left today. Then I asked it, read it again, please. GPT said, I apologize for the inconvenience, for the confusion. If you have started with 10 chocolates and gave 3 to Dr. Imdad, you're still left with 7 chocolates. Then I emphasized that I have 10 chocolates today. And GPT says, I see. My apologies for the oversight. If you have 10 chocolates today and gave 3 to Dr. Andad yesterday, then you currently have 7 chocolates left. So see, this is the kind of quality of answers which we might be getting from GPT or any AI generated stuff. So if I don't know that what will be the number of chocolates I'm left with today, I will have to rely on GPT and I will just take its answer as the correct answer. So, but if I know at the back end that what should be the correct answer, then that's the only way that I can be choosy or I can be selective in picking some of the correct answers of GPT and discarding some of the incorrect answers of GPT. So we should, as a computer science person, we should just know that anything which is being generated by AI is not guaranteed to be 100% accurate in terms of, particularly in terms of the intellectual problems. Okay, so the last data structure, not for today, I'm just introducing this data structure. We won't be like getting into its implementation details because you have bulk of stuff to implement this week. And that structure is called trees. So the kind of data structures which I just summarized, all of them are linear in nature. By linear data structures, we mean that their growth is in one line. So if you just imagine visually that how a linked list looks like, so it grows in one line. How an array looks like, it grows in one line. How a stack looks like, it grows in one line. So those are the linear data structures. And tree is the first non-linear data structure and one of the most important non-linear data structures which we are starting with. So trees are essentially hierarchical representations. By hierarchical representation, we mean that there is a concept of parent and child which comes in. So we have nodes. So there is a node. It can have some number of child nodes. So for example, one top node can have 3 child nodes. So when we say parent and child node, so if A is the parent, then we can have B, C, and D as the child node. So the relationship between A and B is parent-child relationship. C is another child of A, D is another child of B. And same with these nodes can have their own children. So for example, E might be having as E might be child of C and so on. So if you try to get into the terminology further, so there are like terms of ancestor and descendants. So if you look at E has 2 ancestors. C is the immediate parent, A is the grandparent. So A and C are the ancestors of E. And in terms of descendants, so A has different descendants. B, C, D, and E, all of them are actually child or children or grandchildren of A. So they are descendants of A. So then in trees, we have this dedicated top node, which is called root node. So this root node is somewhat equally important as a head is important in a linked list. So this top node is termed as the root node. And the nodes which don't have the child nodes, like E does not have a child node, B does not have a child node. So we call them leaf nodes. Then the nodes which are somewhere in between, like C, they are called internal nodes. So another important thing is that we are using 2 terms over here. So nodes and vertices are interchangeable terms. They are equivalent terms. So vertices is a plural of one node, which is written as vertex. So plural of vertex is vertices, which means many nodes. So they are interchangeable terms. So in this course, we'll be using nodes, vertices interchangeably. So we should just stay comfortable with these terms. By sibling nodes means that they are like children of the same parent. So for example, B, C, D are siblings because they are children of A. Okay. Now, another important thing is the term which we call length of a path. So by path, we mean that if we start from a particular node, how can we reach to another node? So for example, if I start from A, I can go to C, then I can go to E. So this chain is giving me the path. So length of a path, which I just highlighted as green, is 2 because the number of edges in the path is 2. By number of edges, we mean the number of connections, the number of lines. So one connection is between A and C, the other connection is between C and E. So there are 2 connections. So that's what we call edges. Each connection or each line is called one edge. And if there are 2 edges, we call them if there are 2 connections, we call them 2 edges, and we call it length of that particular path. Depth is length of a path from a node to the root or number of ancestors. So for example, if you have to check depth of E, so E has depth 2 because the number of edges which take us from E to parent to the root are 2. But depth of C is 1 because the number of edges which take us from C to A are 1. Same way, depth of B is A, and depth of A itself is 0. Height is another term. So length of the longest branch of a node is height of the tree. So what is the branch? So if you now look at this whole tree, so we have different branches. If we start from A, so this is one branch, which is in orange. If we start from A, we have another branch which is from A to D. If we start from A to C, so this is another branch which is in this purple color. So its branch depth is 2. So height of the tree is length of the longest branch. So if you look over here, so longest branch is from A to E, and its height is going to be the length of this branch. So length of height of the whole tree is 2 because we just measure it as length of the longest branch or longest path which starts from the root node. So these are different terms which we just need to get familiar with because we'll be using them again and again in our coming discussions. So one important thing which I wanted to like emphasize in today's session is that before we go to the next session on trees, which will be a depth or deeper like discussion on trees, including its implementation and some other characteristics, including big O of different operations on trees. We should be very much comfortable with these basic terminologies. So you can see another example printed on the slide of those things, that F is the root node, then G and E are siblings. The nodes which are neither root or leaf nodes, those are internal vertices like G. So A is parent of B, and the leaf nodes are the nodes which don't have any child nodes. So those are like C is a leaf node and so on. And you can see some more illustrations over here in this example, that there is a tree which is rooted at A, and then there are different children of A. Those have like sub-children, and that tree goes down. So let's try to answer some questions. So what are the ancestors of H? Ask yourself and then look for the answers. So let's locate H. So all those nodes which are on the path from H to the root node, they are ancestors of H. So they are D, B, and A. And who are descendants of E? So if you look at E, so all those nodes which are children or grandchildren of E are descendants of E, like I, M, N. What is depth of J? So let's try to locate J. So J is here. So depth of J is the number of edges from J to the root node. So there are 1, 2, 3. So answer is 3. Height of C. So height of C means that if we start from C, so what is the length of the longest branch from C? So if you look at C, there are 2 branches. One goes to G, but the other one goes to F. So the branch which goes to F is the longest branch. Then it goes to J and then P. So if you try to count number of edges in this branch, which is the longest one, they are 3. What is height of O? So O is one of the leaf nodes. It does not have any children. So height of O is 0 because it does not have any child node. So there's no further branch going out from O. And height of A is going to be the number of edges uh, on the longest branch starting from A. So if you look at A, you can take a pause, analyze the branches. There are different branches. Different branches might be having different height. If we try to look at the deepest branch or longest branch, there is A to B, E, I, N. So there are 4 edges on that branch, and that gives us height of A. And what is height of the tree? So height of the tree is same as height of the root node. So root node in this case is A, so height of the tree is also going to be going to be 4. So this was a like very basic nomenclature or terminology and introduction of trees. So we studied some very basic and easy definitions of different terms associated with trees. Please get familiar with them, get comfortable with them before we start and probably we'll try to cover a lot of stuff related to trees in our coming session. So that's it for today from my side. Thank you very much. But if you have all those people who are online, if you have any questions, we can definitely discuss. And if there would be no questions, then we can stop.